Hello, today we're going to be discussing section 12.5. In this section, we are going to talk about lines and planes in three-dimensional space. In two-dimensional space, lines were pretty easy. We could use our formula for our slope-intercept formula, y equals mx plus b. This really covers most lines, though if we do want to include vertical lines, we could use something a little bit more general, something like ax plus by equals c. This kind of an equation will include all possible lines. Unfortunately, in three dimensions, we don't really get lines as easily. Planes aren't too bad. The generalization of this general formula for the line in two-dimensional space essentially becomes our equation for a plane in three-dimensional space. Except we have to include z, of course. So the equation of something like ax plus by plus cz equals d is the equation of a plane. In fact, it will be the general equation for a plane, though we'll get into exactly where the numbers will come from a little bit later. To get to talk about lines is a little bit more complicated. If we're actually going to get the equation of a line, it helps to think about how we actually our slope-intercept form for the line in two-dimensional space. There we had a point, specifically an intercept for our line, though we won't be able to specify that we have an intercept of the same kind of idea in three-dimensional space, but we'll work with a point, and we also work with a slope. Well, not slope in three-dimensional space. Remember, slopes are the thing that's going to play the role of slope is going to be vectors. So we're going to work with vectors. So let's imagine we're talking about a line, and we can say that the line is wherever it is in three-dimensional space. Maybe we'll go ahead and actually draw in some axes. Let's put them in a different color. Say that's our z, our y, and our x. And we have this line somewhere here. Exactly how you want to think of it, actually, how you want to situate it with regard to the axes is up to you. That's not really too important right here. But what we are going to do is we're going to say that we have a vector along the line. I'm just going to draw it above just to make it a little bit more distinct. And let's say this vector is the vector v, and it has components of a, b, c. Now let's say we have a point, let's call it P naught. Naught just refers to the little zero that we're going to put here. And we'll say it's the point x naught, y naught, z naught. We want to get a way to talk about another point, let's call it P, that just has our very general x, y, z coordinates. How are we going to talk about that point? Well, the very first idea is to turn P naught and P into vectors. We're going to think of a vector starting at the origin that ends at our points. So we have a vector here. I'm going to call that R naught. And actually, let me move the notation for P naught. Yeah, the words there were a little in the way. We're going to also draw a vector from the origin over to P. We'll call that R. We like to call these the position vectors of those points. Essentially, it's a way of turning a point into a vector that is frequently kind of useful in Calc 3. And the idea here is that we have a vector from P naught to P. So if we go from that point to that point. And we have a triangle. If we follow R naught and then follow this vector, I should put an arrow over, P naught P, we end up at P. So we basically followed R. In other words, we could say that R is equal to R naught plus P P naught P. That's what a vector addition means. But we also have that P naught P is parallel to the vector V because it's a vector along the line. Now, the way I've drawn it here, it looks like it's in the same direction. It could theoretically be in the opposite direction, but in both cases, what that will mean is that it is a scalar multiple of V. It means either it's a positive scalar multiple if it's in the same direction, or it's a negative scalar multiple if it's in the opposite direction. So you could say that P naught P is some number, let's just call it T, times the vector V. And so we get what we call the vector equation of our line. So here, essentially the coordinates of a point on the line is equal to the coordinates of some point that we know that's on the line already, plus a scalar multiple of a vector along the line. Now, if we do want to turn this into something that's not in vector form, if we don't really want to write them down as vectors, we can go ahead and expand these out. Remember, this r, since it's the vector from the origin to our point, and we can actually turn that into the vector with components x, y, z. Remember, we're just essentially taking the coordinates of our terminal point minus the coordinates of our initial point, but those are just all zeros, so those don't really change anything. So x minus 0 and so on. Same thing with r naught. We're doing the exact same thing, except now we're working with x naught, y naught, z naught. So we have x naught, y naught, z naught. And then we have our t, which t can be whatever number we want it to be. It'll give us another point on the line. But remember, v is the vector ABC. And then we can simplify this. So this side is going to stay the same, but this side, remember, scalar multiplication, we bring that multiple in and multiply the a, b, and c by t. But then we can add components. So this x naught will be added to the t times a. So we have x naught plus ta, y naught plus tb. Well, I should probably put the a and b in front because those are going to be numbers that we're going to have in our problems, and that's what we're more used to 2t instead of t2. This seems a little bit weird to us. So we'll do AT and BT. And then finally, we have Z naught plus CT. And so each of these components, the x, y, and z, actually gives us a different equation. So we have x is x naught plus AT. So that's what we have here. Then we have y equals y naught plus BT, and z has to be z naught plus CT. We call these parametric equations. If you remember from Calc 2, you might have talked about parametric equations in two-dimensional space, where we describe a curve by giving functions for x and y in terms of some parameter t. Well, usually t, sometimes theta, sometimes whatever else you want. Here we're using the parameter t. Well, parametric equations extend very easily to 3 dimensions. Here we just have equations for x, y, and z in terms of our parameter t. These parametric equations are the way that I'll normally try to write down the equation of a line. I find this to be the most straightforward to me. Though we can actually try to eliminate the parameter if we want to. So let's assume for the moment that none of the a, b, and c are 0. Let's just assume that. It gets slightly more complicated if one or more of them is 0. We can't have all 3 of them be 0, or else we don't have a direction for our line. But we can essentially try to eliminate the t. So remember, we start with x is x naught plus AT, there's no reason we can't try to solve this. Essentially, move the x naught over, divide by a, and we get the equation that t is x minus x naught over a. And we can do the same thing for the other one. So here we try solving. We get t is equal to y minus y naught over b. And then the same thing for z. Z minus z naught over c. And the important thing here is that these t's are all the same. They're all the same t. So if we're going to be working with a point on our line, these three quantities have to be the same. So what we get is this little equation here. Well, I say equation, but technically what we have here is two equations. You could say leave off the z minus z naught over c part, and we have one equation here. And then we can leave off the x minus x naught over a part and just have this equation here. You could say, well, maybe set the first one equal to the last one, but if we have those first two that I mentioned, then the third one has to be true anyways. But this is called the symmetric equations of the line. And that's the way you might write it if you don't want to have a parameter t. But I find that this is a little less clear about exactly what's going on. The parametric equations actually kind of just show you, well, here's a direction because you can read off the a, b, and c really easily. And here's a point on the line if you need it. Though you could always pick a different parameter and find a different point if you wanted to. The other problem is, like I said, this is only when a, b, and c are not 0. Obviously here we can't have 0 as one of these, or else things will break a little bit. If one of them is 0, so let's say a equals 0, but b and c are not, then what do we have to do? Well, we'd still kind of go ahead and use the same solving for y and z. So we'd still have t equals y minus y naught over b, and t is z minus z naught over c. But think about what it means for the equation x equals x naught plus at. If a is 0, that equation just becomes x equals x naught. There's no t to solve for. So we'd actually just say, well, this is one of our equations, and then the other equation we get by taking these two and setting them equal to each other. So y minus y naught over b has to equal z minus z naught over c. So here we need both of these two equations, and these would be our symmetric equations for this line where a is equal to 0. So note in both these cases, and in fact every case you're going to be seeing, you cannot describe a line with one single equation. Well, at least not without vectors. We have two equations to actually determine what a line does. And when you get into it, it basically is what we're doing here is thinking about the intersection of two planes to get our line. Though that you can think about it a little bit to try to figure out why that makes sense after we talk about planes in the next video. But I only really bring up symmetric equations here because some of the online homework questions will ask you for symmetric equations. Like I said, I do just prefer using the parametric ones because they make a little more sense to me. But if you want to use symmetric equations, there they are. Let's work through a few problems from the book. So here we're asked to find parametric equations and symmetric equations for a particular line, and they give us some information about the line. So you might notice right away that we don't have the information that we kind of started with when we first described how to find the vector equation. There we had a vector along the line, and we had a point. Here we're just given 2 points. Think about it how if we were working with a line in two-dimensional space, which we don't know the slope, but we have 2 points in the line, what would you do? Well, there the first thing you'd do is try to find the slope. Here what we're going to do is try to find a vector. can we find a vector that points along the line? Well, we basically have our 2 points. We want to line through them, so let's first just find the vector between them. So we're just going to find a vector, let's say from this first point here, which, I don't know, maybe we'll call it P1, to this point here, P2. Now let's call the vector V, which is just P1, P2 with an arrow over it. Remember how we do that? We take the coordinates of our terminal point minus the coordinates of our initial point. Our terminal point here is P2, so we'll take 2, this x coordinate, minus this x coordinate here, so 2 minus 0. And we have 1 minus 1/2. And finally, negative 3 minus 1. Or ultimately, what we have? We have 2, we have 1/2, and we have a negative 4. That is a vector along the line. It's not the only vector. Obviously, we could have any multiple of this vector would still work, and we could form our parametric equations using any of those vectors if we want to. And we can also pick whatever point we want. I'm going to go ahead and pick P1 as my point, and then I'm just going to use those. So what do we have here? Well, remember, this is the A, B, and C, and so this would be the x0, y0, z0. So we have x is x0, which is 0, plus A times t. Going to leave off the 0 there, of course. Y is going to be y0, which is 1/2, plus B, which is 1/2, times t. And then finally, z is z0, which in this case is 1, then plus c, or minus 4, times t. These would be our parametric equations. Oops. My U looked like an A, and I didn't want the confusion there. Okay. These are the parametric equations for this line. Obviously, like I said, these aren't the only possibilities. We could have any scalar multiple of our vector, and pick any point that we know, so either P1 or P2 in this case, and we get different equations technically, and that just refers to having a slightly different parameter in its technical sense. It'll still describe the same line. They also want us to give symmetric equations. So what would we do there? Well, we imagine solving each of these for t. So if we solved x equals, well, just 2t, for t, we'll have t is x over 2. If we solve y equals 1/2 plus 1/2 t for y, we would have y minus 1/2, and then divided by 1/2 would equal t. We could simplify this a little bit if we want to. And then finally, if we solve this one, we have z minus 1 over negative 4 is equal to t. Again, if we wanted to, we could solve that as well. We could simplify this down to x over 2 is 2y minus 1, and we could say, I don't know, let's say 1 minus z over 4. If we don't want to have a negative in the denominator. But really, either one of these works. Could say this first one is the kind of the default symmetric equation. Okay. Here's problem 9. We're asking the same problem, or the same instructions here, and again we have 2 points. But just because we really want to make sure that we know this, let's just do another example of it. We're looking for a line through these 2 points. Again, we can pick what. I'm just going to call them P1 and P2 just to make it easier to refer to them. We find a vector along the line, which, again, we could pick whichever order we want. I'm going to go ahead and do P1 to P2 again. That means I'm going to subtract our coordinates, so 3 minus negative 8, or basically just 3 plus 8. then negative 2 minus 1, and 4 minus 4. So our vector just becomes 11, negative 3, 0. Zeros are nice. Again, we pick one of the points. I'm going to go ahead and pick P1, just because. And then we form our parametric equations. So x is going to be the x-coordinate, negative 8, plus the first component of our vector times t. Y is going to be our y-coordinate of our point, so 1, plus, well, minus 3 times t. And then finally, z is going to be the z-coordinate, 4. But then we just have a plus 0t, or really this is just z equals 4. Again, these are our parametric equations. To get the symmetric equations, what we would do is we'd solve these equations for t. So the first one, we'd bring the 8 over, the negative 8 over, so we have x plus 8, and we divide it by 11, is equal to, now we'd say y minus 1, and we divide it by negative 3. But again, with the z equation, we do not have the ability to solve for t. There's technically no t's here. So what we're going to have to do is leave the z equation how it is. We just have this equation here and z equals 4. This would be our symmetric equation for this line. Essentially, the fact that the z coordinates are always 4 is important. They all are in this plane of z equals 4. So they're all kind of horizontal lines, though saying it's horizontal is a little ambiguous when we're talking about three-dimensional space. But it's just a flat horizontal line in some particular orientation. Let's look at one last problem, or at least for lines. We'll look at some more problems when we talk about planes in the next video. But here, same directions. But we do not have the same situation. We do not have 2 points in the line, so we're going to have to think it through a little bit more. We have a line through a particular point, 2, 1, 0, and perpendicular to two given vectors. Now, we don't have a vector that's along the line right now. How are we going to get a vector that points along the line? Well, such a vector is going to have to be perpendicular to both of these two vectors. And we have to think about how we would get a vector that's perpendicular to two vectors. That's where our cross product comes in. We're going to have to take the cross product of I plus j and j plus k in order to get our vector along the line. So I plus j crossed with j plus k. And we're going to have to figure out how to do that. Well, just as a reminder, I like to go ahead and think of the cycle of ijk and think about what happens when I multiply those together. Essentially here, I can expand this out, this product. Just think about it in the normal foiling method, but just remember that we do not want to swap the order of our multiplication. So you can say this is I crossed with j plus I crossed with k plus j crossed with j plus j crossed with k. Now what are those? Well, I crossed with j, we follow the arrows to go to j, which means we end up at k. Then we have I to k, but now we're going against the arrows, so we end up at j, but a negative j. J crossed with j, well, a vector crossed with itself is always 0, so that one just goes away. And then j crossed with k, well, j to k, we're following the arrows to I, so we get a positive I. And if you prefer, we can go ahead and then put these into our normal angle brackets. So we just have an I here. That's a 1 in the x coordinate or the x component. Then we have a negative j, so that's a negative 1 here. And then we have a k, which is a positive 1 there. So this is a vector along the line, and well, we only have 1 point to work with, so that's the one we're going to have to use. So what do we have? We have x is our x coordinate of 2 plus 1 times t, so just plus a t. Y is going to be our y coordinate of 1 plus a negative 1 times t, so minus t. Then finally z, well, our z coordinate is 0, so that's what leave it as 0. We'll just leave that one out. But then we have plus 1 times t, so z is t in fact. So these are our parametric equations. To get the symmetric equations, again, we look at these and we imagine solving for t. So the first one, we just subtract 2 from both sides. We have x minus 2. Then we have, well, y minus 1, but then divided by negative 1. And then finally here, there's not really any solving to do. It's just going to equal z. Or in other words, let's go ahead and simplify this middle one. We have x minus 2 is equal to 1 minus y is equal to z. So these symmetric equations actually look really nice. They don't have any fractions involved anymore. But that's what you'd have to do. You have to figure out some way of getting a vector along the line given the information that you have. Whether or not you have 2 points, in which case you just have to find the vector between those 2 points, or in this particular case, we know something that's perpendicular to, and so we have to use the cross product in order to find a vector. But it's really the main point is to find this vector. They're going to have to give you a point on the line, or some way to find a point on the line. It's usually finding the vector that's the tricky part. So again, there's going to be problems like this on your homework. Try them out. If you have any questions about any of them, you can always see me in my office hours. But I'm going to leave that for now. In the next video, we'll talk about planes. So see you there.